Next speaker is Frank Hutter. He's a professor in the Department of Computer Science in the University of Freiburg, Germany. Frank is very well known for his work in Bayesian optimization, and last year your team won the competition of AutoML, right? Yeah, that's an amazing achievement, and Frank is here to tell us more about his work on Bayesian optimization and automatic machine learning, AutoML. Yeah.
Thank you very much for this nice introduction and for the invitation. Yeah. Okay, so I'll be talking about AutoML and how to speed it up. To motivate AutoML, we already heard some in the beginning from Quark, but let's look at how the current deep learning practice happens for when a machine learning expert wants to fit a model on a new data set. So first, they need to decide which architecture to use and set some hyperparameters, and then they can run their deep neural network. But typically, the very first time they run it, something comes out that they're not quite happy with. Maybe learning diverged or some other hyperparameters weren't set quite right. So they do need to iterate, and this becomes an iterative manual process of actually looking at your architectures and hyperparameters. And this process also depends a lot on how good this machine learning expert actually is, how much expertise they have and how much experience they have built up over years in this art of deep learning that has also been called alchemy earlier this week. And what we're trying to do is to move from this art more towards a principled engineering science that lets us define when to use which sorts of methods. And that can also lead to, in the end, true end-to-end learning. By which I mean the data goes in, you press a button, and then the machine learns. Because in the end, it's called machine learning and not human expert learns about how the machine learning method works. So this end-to-end learning can, of course, be implemented by some sort of meta-level learning and optimization that learns about this learning box and optimizes this learning box. And basically, as Quark said, automates the machine learning expert. One way of treating AutoML, one way of solving it is as a black box optimization problem. So that would just replace this learning box by a black box, and in goes some hyperparameter vector lambda, and this lambda can be an object that's actually structured. It can have all kinds of, it can be a neural network structure, so there can be a lot of structure in there. It doesn't have to just be continuous hyperparameters. And outcomes an f of lambda, that's a performance of this neural network. And then we can use our favorite black box optimization methods, and today we happen to talk about evolutionary methods and about reinforcement learning and about Bayesian optimization, and all of these could be used in order to optimize this black box function. I'm actually very pragmatic about which method to use. I've used all of them, but I guess today I'm here representing the faction of Bayesian optimization. So I do want to take 1 minute to clear up one misunderstanding about Bayesian optimization, which kind of is due to, well, happened after a blog post from Ben Resch last year, in which he talked about a really nice method, hyperband. But as part of that blog post, he also mentioned that sometimes Bayesian optimization is not actually more than twice as fast as random search. And that's absolutely true. I was not surprised by that. Somehow a lot of people were. Sometimes Bayesian optimization is not more than twice as fast than random search. Sometimes actually in the beginning of the search, when you know nothing, Bayesian optimization is not faster than random search at all. It needs to explore the space first and kind of figure out where to go downhill and then learn something about the response surface, and then figures out how to get to the global optimum, and then start speeding up a lot. So as time goes by, typically we see that Bayesian optimization does a lot better than random search. And this can also be quite dramatic, so sometimes we really see orders of magnitude speed-ups over Bayesian optimization, over random search. Note that this is actually not only the case for Bayesian optimization. Here's a figure that Kwok will recognize. It's from his paper, Neural Architecture Search by Reinforcement Learning. And we see that up to 1,200 function evaluations, reinforcement learning was not better than random search here. But with larger budgets, of course, there's greater and greater improvements. And that's what you would want from any reasonable optimizer. So this is a positive result. And nobody would go and say, look at the first 1,200 function evaluations. Oh, reinforcement learning is not better than random search. That would be the wrong conclusion to draw from this figure. That's pretty much all I want to say about Bayesian optimization versus reinforcement learning versus evolutionary methods. In the rest of the talk, I will be using Bayesian optimization, but most of where I'm going in this talk is actually very much in line with Ben Recht's post on hyperband, that we should not necessarily limit ourselves to this black box view, because this black box view is very limiting. And a lot of people in Bayesian optimization actually do use this black box view, and kind of the first sentence in the paper is, let f be a black box function. And well, yes, it can be a black box function, but it can be more than a black box function. And if we treat hyperparameter optimization of deep neural networks as a black box, then, well, a single function evaluation will just take weeks. And that's a little slow. Of course, we can parallelize this, also Bayesian optimization, but it's just not the most efficient use of time. Okay, so I do want to talk about, very briefly, 3 AutoML systems, and while I talk about them, give hints on 6 ways of how to go beyond black box optimization. And I'll denote these by these little symbols. So the benchmark here is this AutoML challenge that Kwok mentioned. This was a very large-scale challenge, 1.5 years, organized by ChaLearn and CodaLab by Isabelle Gouillon. There were 2 tracks, code submissions and a Kaggle-like human track. And the code submissions are the most interesting part. There, you really needed true end-to-end learning. So you submitted a system that reads some training data, builds a model, and predicts on test data, all end-to-end without any human in the loop. There were 25 data sets, and one thing in the challenge was they were already featureized, so deep learning did not play a very large role. And because a lot of data sets out in the real world are already featureized, what we did actually back then first for AutoML was to parameterize the framework Weka, which is a machine learning toolbox in Java that's probably not very well known in this community, but it's heavily used in the life sciences, for example, and Weka has something like 30,000 citations. So it implements a lot of different machine learning classifiers, and each of them have a lot of hyperparameters as ensemble methods, and if you parameterize it, you end up with something like 786 hyperparameters. And what we did back then is simply see what happens if we just optimize cross-validation performance by Bayesian optimization. Here, the first speed-up trick comes in. This is cross-validation performance. We know that cross-validation performance is an average of the individual performance of the folds. If we have 10 folds and on the first fold our parameter configuration is already very poor, then it doesn't make a lot of sense to evaluate the other 9 folds, but we would rather want to move on and save time. So you basically have a little mini bandit for every configuration. And if we exploit that, then we can actually get 5-fold speedups for 10-fold cross-validation. One nice thing working in AutoML that allows us to actually put software online that a lot of people can directly use, that don't maybe know machine learning, or that haven't taken a lot of machine learning courses, that are not experts, but they can just use it out of the box. The second system is AutoScaLearn, so that's actually fairly similar, but it parameterizes the scikit-learn toolbox. One other speed-up trick we use here is through meta-learning or reasoning across data sets. Given a new data set, we looked at how similar are previous data sets we've seen before, and what were good algorithms and hyperparameter settings for those, and run those first in order to kind of bootstrap and get us a very nice initialization for Bayesian optimization. And that really does dramatically speed up the search. Also, when you run Bayesian optimization, you get all these different function evaluations, you have all these different models, and it would be kind of sad to only return a point estimate in the end. That's not very Bayesian. You would rather want to return some sort of ensemble, and you can build these ensembles basically for free. And in particular for small data sets, that actually helps you a lot with robustness. AutoSQL as Prof mentioned, did win this competition. It's really ready for prime time. There was the automated statistician, a variant of that by James Lloyd, was in the competition for the first 2 phases and was really head-to-head, so it was great, and then they dropped out. So then after that, it was really easy. So AutoSQL is a plugin replacement for scikit-learn estimators. And you can use it in 4 lines of code, and basically here you just put in your X train, Y train. This line here will run as long as you tell it to run, maybe a day. And then you have a predictor. This is an open source project, so if you feel inspired, please contribute. That would be very nice. The third system is AutoNet, so we parameterize deep neural networks, did network architectures and hyperparameters. For the AutoML challenge, that's the only instantiation I have time to talk about right now. There we had featureized data, so we had really kind of boring networks, just up to 5 layers, fully connected, only 29 hyperparameters, and we optimize it on less than a day and 5 GPUs. And actually, AutoNet did win several data sets against human experts in this human track. And to the best of my knowledge, that's actually the first automated deep learning system to win a machine learning competition data set against human experts. But AutoNet is still kind of working a lot on the black box, so kind of evaluating cross-validation performance is still relatively slow. And for large data sets, that wouldn't really scale up. So for large data sets, what you can do is to work on cheap approximations of this black box. So visualized by this. Here we see a response surface of an SVM fit on MNIST. This is the whole MNIST data set, 50,000 data points, and this is 400 data points. And we see that the response surfaces actually look qualitatively quite similar, but we can evaluate this cheap black box here about 10,000 times faster than this black box. So we can do a lot of our work on the cheap black box and then slowly work our way up. In this case, we use Bayesian optimization to have another dimension in there, which is the size of the data set, and got up to 10,000, up to 1,000-fold speedups for large data sets. For ConvNets, we only got up to 10-fold speedups because they only scale linearly in the number of data points. Another way to approximate the black box is to closer to the microphone. I already got a feedback, so I don't think that's a good idea. Do you hear me? Okay, it improves it for you. I hear a really bad echo. So I will try. It's quite irritating. So another way to approximate the black box is to work with less epochs. So if we have hyperparameter settings that are poor, then sometimes you get learning curves like this. And of course, we want to cut these off. So we can use a model to predict when a learning curve will not be very good and cut it off, and then have kind of a model-based early termination criterion like this that qualitatively and quantitatively leads to some speedups. I promised to talk a little bit about hyperband. So this is a way to actually combine these different ways of thinking about approximate black boxes. So it has this notion of a budget, and it starts with a small budget. The budget could be number of function evaluations, or it could be a subset of the data, or a number of epochs. And it starts with a lot of configurations for a small budget, and then iteratively selects the top half of these configurations and gives it double the budget. And that of course puts a lot of, lets us explore a lot of configurations for very cheap. Hyperband basically is a wrapper around successive halving that starts with different trade-offs of the number of configurations and the budgets. And what we see in practice for hyperband is that because it spends a lot of effort on these approximate black boxes, it's very good in terms of anytime performance. So here, comparing to random search, in the beginning, we actually get a speed up of 20-fold. And in the end, well, it's only a 3-fold speed up because, well, also hyperband does evaluate on the full black box at some point, and then at some point the speed ups are not that large anymore. If you remember from the beginning, Bayesian optimization is the reverse. In the beginning, we don't have a speed up over random search because we start evaluating with a full black box. But over time, as we explore the space, we can actually basically follow gradients and get good evaluations quickly. So the two are very complementary, and it made a lot of sense to combine the best of both worlds, so that's what we did in actually a workshop paper here. So this is also very new, not from yesterday night, but from 2 weeks ago. And get strong anytime and final performance. Okay, yeah, we can also parallelize this. This parallelizes beautifully, so it's also a myth that Bayesian optimization doesn't parallelize. One has to work a little bit harder, and it doesn't parallelize perfectly, but almost perfectly. So with 8 workers, we get 7.5-fold speedups here. We use this. Being a research lab, we don't have 800 GPUs, but so we tried to tune CNNs on a budget. So we said, okay, the maximum budget is you can use 2 hours on a Titan X. And then we ran this procedure Bob for 12 hours on 10 GPUs, and the end result actually had a test error of 4%. We ran this again with a budget of 3 hours for a Titan X, and then got down to 3.5%. So within 3 hours, you can get to 3.5%, and you use a total budget of 12 hours on 10 GPUs, so that's an equivalent of about 40 full function evaluations. And we're trying to push this further to the point where you might only need an equivalent of 5 function evaluations or so. Okay, so the 6th and final way to go beyond black box optimization is to adapt your hyperparameters and your architecture online during the search. So to go beyond starting from scratch with every single hyperparameter configuration. The way you can do this in architecture space is by exploiting network morphisms, which work as follows. So you have a current model with some partially trained weights. We denote the architecture here by these four bars. And we, for example, make one layer wider. In this child here, we put an additional layer in. Here we maybe add the skip connection. And these network morphisms allow us to get the same function as before. So we instantiate the new weights here in order to keep the same function. So for example, it's just an identity mapping for a new layer. And then in the next step, you can train each of these child networks for a little bit, and we found a very quick cosine annealing to already yield large improvements sometimes. And then look at the performance of each of the individual models, pick the best one, and then iterate this process. And of course, you could pick a couple of best ones and have a beam search like this. Yeah, and so you then iterate that, and iteratively you make layers wider, or add a layer, or add skip connections, etc. And by not optimizing each of these networks from scratch, but by exploiting this partially pre-trained networks, we can actually do architecture search on a single GPU in half a day that gets us at least 5.7% on CFAR. And of course, this process here parallelizes beautifully. So if we add more resources to this, I'm actually quite confident that this could lead to new state-of-the-art performance in the future. We're not there yet, but I think this is actually a really exciting area to look at. Okay, with that, let me conclude. So Bayesian optimization enables some true end-to-end learning. I showed these 3 different AutoML systems. And we can get large speedups by going beyond just black box optimization. And Bayesian optimization is not limited to black box optimization. We have links to code online, and I'll thank you for your attention. Questions?
So you briefly talked about using, I guess, function evaluations from previous data sets as a way of worm sorting. So I'm wondering how much that depends on the similarity of the previous data sets to the current data set.
Okay, very good question. It definitely depends on the similarity of previous data sets to the current ones. So what we do is actually, in this particular setting, we actually looked at a lot of different data sets that we had run on in the past and had a similarity metric between data sets using meta features, and started from the data sets that started from the configuration that were best on the data sets that were closest You can also just start from configurations that are good on average, and that also already works quite well. So, but good question. Thank you.
A great talk. I'm Venkat from Oracle Labs. So one of the challenges in all these AutoML technologies is that you often, when you tune your models, you may overfit to your training data. What are your experience in that, and how you propose to solve those issues when you end up overfitting?
Right. So if you have small data sets, then overfitting is definitely a problem. We just have a very large design space here, and we search that automatically. So we have cross-validation, of course, to guard a little bit against overfitting, but that only goes a certain distance. What we definitely did find is that Bayesian optimization overfits less than something like grid search, because grid search has no regularizer in there. So Bayesian optimization evaluates a lot more models in areas where other points were working well. So you get an implicit regularization in there. Whereas in grid search, you just take the best of all these different samples. But still, if you have 100 data points, I would say do not use auto-scikit-learn. It's just not going to work very well on that. So it's not a silver bullet. I don't want to come across that way.
Thank you.
I should notice, if you have only 100 data points, you can still use AutoSQL-learn with some limitations. So you can say only use an LDA or only use a very limited part of it, and that's in the API. So, but if you have really little data and you're worried about overfitting, then that is something that should be done. Thank you.
Thank you, speakers, for the great talks. I think we're going to take a break, and then we're going to resume at 4:30.